The landing stage of flight is defined as being that stage of flight commencing from 50 feet above the landing threshold and terminating when the aeroplane comes to a complete stop. The 50 feet point is sometimes referred to as the landing screen height. The landing screen height is fixed at 50 feet for all classes of aeroplane, unlike the takeoff screen height, which is 35 feet for Class A aeroplanes and 50 feet for Class B aeroplanes. At the landing screen height, the aeroplane must have attained the landing reference speed known as Vref. Vref for Class A aeroplanes must be no less than the greater of 1.23 times the stall reference speed in the landing configuration, and the velocity of minimum control in the landing configuration. Vref for all other classes of aeroplane must be no less than 1.3 times the stall speed in the landing configuration. Vref is a very important speed to attain, since the landing distances in the aeroplane flight manual are based on aeroplanes flying at Vref. Therefore, if a landing aeroplane is not at Vref, the landing distance given by the manual will not be achieved by the pilot. A landing carried out at a speed other than Vref could seriously jeopardize the safety of the landing. The landing can be divided into two parts. We call these the airborne section and the ground run or landing roll. The first part, the airborne section, starts from the landing screen height of 50 feet and ends when the aeroplane's main wheels touch the landing surface. The airborne section is usually given as being about 1,000 feet in length. Within the airborne section, certain critical actions take place. On descending through the screen height, the thrust is reduced to 0, and the aeroplane pitch attitude is increased slightly so that the aeroplane is in a slight nose-up attitude. The increase in pitch attitude helps to arrest the rate of descent, and the reduction in thrust to 0 reduces the speed. This procedure of reducing thrust and increasing pitch is known as the landing flare, although other terms like a round-out are commonly used. The landing flare will allow the aeroplane to touch down onto the runway using the main wheels first. It is important to understand that the technique of flaring the aeroplane differs from one aeroplane to another, and especially so between light general aviation aeroplanes and large commercial jet airliners. The second part of the landing is the ground run or landing roll. This is the distance covered from touchdown until the aeroplane comes to a full stop. As with the airborne section, there are a few critical actions that are carried out. Once the main wheels have settled onto the landing surface, reverse thrust and lift spoilers can be activated, and as the speed decreases further, the nose wheel will then settle onto the landing surface. Braking force is now applied, and the aeroplane will slow to a stop. However, in normal operations, the aeroplane does not stop on the runway. Rather, the aeroplane is slowed to a safe speed where it can then be steered off the runway and taxied to the disembarkation point or ramp. The combined length of the airborne section and the ground run or landing roll is known as the landing distance required. Pilots need to make sure that the landing distance required does not exceed the available landing distance. In order to better understand landing performance, we need to analyse the forces acting upon the aeroplane, and how these forces might be modified throughout the landing. The first of the forces that we will consider is weight. As you have learnt already, weight acts vertically downwards towards the centre of the Earth from the centre of gravity. During flight, weight is mainly balanced by lift. However, once the aeroplane is on the ground, weight is balanced by the reaction of the ground acting up through the wheels on the undercarriage. The weight of the aeroplane on landing will be less than at takeoff due to the fact that fuel has been consumed. There is, however, a maximum structural landing mass which must not be exceeded. Let's now consider lift. Whilst lift helps to balance weight when in the air, once the aeroplane is on the ground, lift is no longer required. In fact, during the landing roll, lift is detrimental to the landing performance. Producing lift will reduce the load placed on wheels and therefore decrease the braking effect. In large commercial aeroplanes, once the main wheels have settled on the runway, the lift spoilers or lift dumpers are deployed, which act very quickly to disrupt the airflow over the wing and destroy lift. Whilst in level flight, the forward-acting force of thrust is essential to maintain sufficient speed for the wings to provide lift. During landing, because the aim is to bring the aeroplane to a stop, the thrust force must be reduced to zero. Any residual thrust would be detrimental to the landing performance. However, large propeller and jet aeroplane engines have the capability of redirecting the force of thrust in order to generate a braking effect on the aeroplane. This is known as reverse thrust. Reverse thrust helps to reduce the aeroplane's forward speed. Reverse thrust capability is especially important in conditions where braking force is reduced due to ice or water contamination on the runway. Jet engines produce reverse thrust by using one of several methods, but all jet engines follow the same basic principle, which is to redirect the jet efflux in a forwards direction. This animation shows an example of a jet engine in reverse thrust mode. Many modern aeroplanes have a safety device whereby reverse thrust is not activated until a certain value of the aeroplane's weight is pressing down on the main wheels, and until the wheels have reached a certain speed of rotation. Once the aeroplane's reverse thrust system has detected this, reverse thrust is activated, and the engine will reconfigure itself so that the exhaust gas flow can be redirected forwards. However, pilots need to recognize that the process of getting the engines reconfigured to generate full reverse thrust takes time, and so the aeroplane will have travelled a small distance from the touchdown point before reverse thrust takes effect. This fact reduces the effective time period during which reverse thrust can be used. Therefore, the effectiveness of reverse thrust on landing is reduced. It is important to note too that jet engine reverse thrust cannot be maintained right up to the point when the aeroplane comes to a full stop. Reverse thrust must be deactivated before the forward speed reduces to a minimum value. As the aeroplane slows down, the redirected airflow may start to be re-ingested into the compressor, as shown on screen. This means that the jet engine recycles its own gas flow, which significantly increases the engine temperatures. But it also means that debris on the runway can be sucked into the engine, potentially causing major damage. As a result of this danger to the engines at low forward speeds, reverse thrust must be deactivated below about 50 knots. The combined effect of late reverse thrust activation and early reverse thrust deactivation means that the time period for which reverse thrust can be used may be quite short. Large turbopropeller aeroplanes are also able to generate reverse thrust by redirecting the airflow forwards, but they do so in a very different way than that employed by a jet engine. For forward flight, the propeller blade is angled in such a way as to displace air backwards, thus producing forward thrust. This produces a forward force, as shown. In order for the propeller blade to direct air forwards and create a rearward acting force, the blade angle must change to the position illustrated here. The blade angle required for the propeller to generate reverse thrust is known as reverse pitch. Because only a change of blade angle is required, a propeller aeroplane can switch from forward to reverse thrust far quicker than a jet aeroplane. This means that a propeller aeroplane can use reverse thrust earlier in the landing roll than a jet aeroplane. A propeller aeroplane can also maintain reverse thrust until the aeroplane comes to a full stop. This capability gives the propeller aeroplane a greater braking advantage over the jet aeroplane during landing. In summary, the usable period of reverse thrust in the landing roll is shorter for a jet aeroplane than for a propeller aeroplane. For this reason, the authorities have laid down less stringent landing performance regulations for propeller aeroplanes. The precise nature of these regulations will be discussed later. However, it is important to note here that when calculating the landing distance to comply with the landing regulations, the use of reverse thrust is not considered except when the runway is wet. Therefore, when reverse thrust is used, the landing distance achieved should be considerably less than the calculated landing distance. Let us now consider the action of the drag force during landing. You may recall that there are several forms of drag. The main types of drag are parasite drag and induced drag. However, whilst the aeroplane is on the ground, during takeoff and landing, wheel drag must be considered alongside the aerodynamic drag just mentioned. The aim of the landing is to bring the aeroplane to a stop safely within the confines of the runway. In order to decelerate, sufficient rearward directed forces need to act on the aeroplane. Consequently, in addition to reverse thrust, aerodynamic drag plays a very crucial role in landing. Of the two types of aerodynamic drag, we'll deal with induced drag first. Induced drag is dependent on lift and is proportional to angle of attack. During the airborne section of the landing, there is still a large amount of lift being generated, and the angle of attack is relatively high. This means that induced drag is far higher than in cruising flight. However, when the aeroplane nose wheel touches the runway, the angle of attack is almost nil. Induced drag is consequently reduced to almost zero. The second form of aerodynamic drag is parasite drag. Parasite drag is a function of the aeroplane's forward-facing cross-sectional area, more accurately known as form drag, and of the aeroplane's forward speed. The configuration of the aeroplane for landing is such that the flaps and slats are fully extended, which significantly increases the aeroplane's form drag, and therefore significantly increases parasite drag. Once the aeroplane touches down and the spoilers and speed brakes are deployed, parasite drag increases even further. However, as the speed rapidly decays after touchdown, so will the parasite drag, eventually decreasing to zero once the aeroplane reaches a full stop. In summary then, the aerodynamic drag comprising induced drag and parasite drag will be very high during the early part of the landing, but very soon after touchdown will decay rapidly.